All right. So this session is about is part of the series of the live Qiskit sessions on basically on the broad topic of quantum circuits, and what I'm going to talk about today is this recent addition to Qiskit, which is a circuit library. And I'm going to talk about its significance, why you might care about a library of different circuits, and I'll basically just go through some examples. It starts very simple and might get more advanced towards the end. If there are any questions on any aspect of it, just again type in the chat box. Hopefully, I'll see it. Yeah, and then hopefully towards the end there'll be more time for Q&A. All right, so a very common question I get from people who are basically starting to learn about quantum computing, especially people who have a background in classical programming, classical computing, is how do you do very basic things on a quantum computer? Like how do you even add 1 + 1 to get the answer 2, right? If I'm on my laptop right now, I can just pull up Python, and I can literally type 1 + 1, and I can execute the cell, and ta-da, I get 2, right? So what's happening here is that this is Python is giving you layers of abstraction over what is actually going on your computer. So basically, when you type 1 + 1, this expression gets parsed by the Python interpreter. It gets lowered down to bytecode. It gets sent to loaded into memory. It gets executed on the processor, and the answer comes back to you, right? But hopefully, as a programmer, you don't want to care about those details. Like you don't want to care about the execution model, the pipeline of flow of information through the processor, the transistors, et cetera, right? This model is clearly a very classical model. If I want to do a similar thing on a quantum computer, you might say, all right, so let's break down the problem, right? So I want to add two numbers. This sounds like an adder. Like if you're familiar with like classical logic, Boolean logic, FPGAs, right? You can express these things as truth tables, essentially. Like you have two inputs, A and B. So each of these are 1 bit for this very simple case. So the inputs can be 0, 0, 0, 1, 1, 0, 1, 1. These are the things that I want to add together. And then what I get is a sum and a carry bit, right? That's like the very simple adder. And so in a classical logic circuit, I can represent this with this kind of thing, right? So I basically say, here's my input. The sum is basically an XOR. If both of them are 0 or both of them are 1, it becomes 0. If one of them is exclusively 1, it becomes 1. So I have an XOR gate. And for the carry, I can basically use an AND gate to give me the carry. So this is the adder circuit. This is the half adder circuit, right? Classically. However, this doesn't run as is on a quantum computer. There are some issues with this, right? So one constraint on quantum computing is that the circuit that you're building, again, we call it circuit, very similar to this model, right? It's called a quantum circuit. But a quantum circuit has to be reversible. And this goes back to, for example, you have you can represent the state of qubits as a vector in a space, and the operations that you do on this vector is basically moving the vector around, but it has to be essentially give you still a valid state, so it has to be norm preserving. It has to because the probabilities all have to add to 1, and so in order to get this norm preserving behavior, you have unitary matrices which are reversible, blah blah blah. Right, so this doesn't run as is on a quantum computer. I have to modify the circuit to become a valid quantum circuit. So how can I do this? So in Qiskit, I can basically code this up from scratch. So I load up from Qiskit a quantum register, a quantum circuit object. So essentially, Qiskit is Python, right? So I built 3 registers. I need 1 extra register in order to make this circuit reversible. And what I do is basically I create this ancilla bit, essentially what is called. I put it in the 0 state, and then I do what I need to do. So this AND is not a reversible operation. In order to make it reversible, you use this gate called the Toffoli gate. So it's a 3 input 3 output where it basically takes the AND of its control bits, and the XOR is basically just a regular C0, right? So this circuit is basically doing that addition. It's basically doing the XOR and the AND. And then you can actually test it. So in Qiskit, you can use a simulator. So here I'm using this quantum information submodule of Qiskit, which is quite nice. It like allows me to test in different send in different inputs and see the effect on the output. So for example, I set up different states for these qubits. So because these are no longer just regular bits. These are qubits with a quantum state. So each of them has an associated state vector with it. So I make a state for A, B, and C from integers, because you can encode any integer into some number of qubits. So I assign them state 1, 1, and 0, right? And then I basically say, all right, so this whole thing, this 3-qubit subspace, 3-qubit space, is the state A expanded, essentially tensor order, expanded with state B and expanded with state C. I evolve this state through this adder that I built, and I get an output state. And then I basically I'm interested in two of the bits, the carry bit and the sum bit, which are basically these things, right? And then this is what I get. So if I feed it 1 and 1, I get a carry of 1 and a sum of 0. I basically get 2, right? So I can change this to whatever I want. If I give it 0, 1, I read 0, 1, and this is the probability of the measurement. So this is a quantum computer now. It's no longer classical. There are probabilities associated with each observation. So again, basically, if I give it 0, 0, I read 0, 0 with probability 1, right? So I basically now I broke down the problem of addition. I built it out of gates. I tested it. It works, right? But hopefully, as a programmer, you want to use addition in, you want to be able to reason about computation at a much higher level, right? You don't want to care about all of these details every time. So yeah, would it be nice if I could just use an adder without worrying about all these details, right? And it turns out the problem of addition on a quantum computer is very well studied. So this is one example from the literature. I built it into the Qiskit circuit library for the purpose of this talk. It's basically an adder by Kukuro and let's see, Draper and Putin and Moulton, I think. The 4 authors, but basically this is the figure from the paper. It basically uses some majority of 3 bits. It propagates it in a ripple carry adder fashion, and then it does on computation to get, and it copies the answer is here. But anyway, this is using this is as simple as basically getting it from the Qiskit circuit library and instantiating it. So now I'm instantiating with 4 qubits, meaning it does addition on 2 registers of each size 4 qubits. And this is how it works. So again, I'm doing the same simulation. I set up some state vectors. This is the figure automatically drawn from the library that I grab it from. And I encode 2 numbers into my state. So I encode, for example, 6 and 9. And so again, so these are from integers, but they actually become bits that go into the inputs. So A contains the number 6, B contains the number 9. There's a carry in and there's a carry out. So this is a full adder, right? And actually, I read out the number 15 with a probability of 100% again. So I compared the readout is actually, if you run it on a quantum computer, you're reading out bit by bit, but you just basically, here I convert it to an integer just to demonstrate that, this is the addition that I'm looking for. And I can change this. I can change this to 5 and whatever, 2. And I get 7. Right, so this is a fairly complex circuit with that does addition for me, and then you can say, all right, so what about, maybe there are some other ways to add, and in fact this problem is really well studied. There are many types of adders. There are adders for if you care about if you have a continuous gate set, if there are adders that are optimized for example, if you have a fault tolerant computer, blah blah blah. So for example, there's another type of the adder. So for example, if the circuit library could also contain this type of adder, a Draper adder. It's basically based on Fourier transformation. So this figure again is from the paper, and this is how it gets drawn in Qiskit. What you do is basically you transform one of the input registers into the Fourier space. Then you do a bunch of control phase gates, and then you do an inverse Fourier transform. And again, so you can make these any numbers that you want, and you get the sum of those in here. And then the nice thing about the library is that the library could take care of making this robust implementations for you, so you don't have to make them from scratch. It can optimize them for you, and then when these exist in the library, the compiler, for example, can have more knowledge about how to optimize them, for example. Let me see if there are any particular questions on this. can you modify Qiskit to make a semi-classical program? What do you mean by semi-classical, I guess? I'm not sure. Oh, wait. So in the about the semi-classical program, I guess. So in principle, any computation you do on a classical computer, you should be able to do it on a quantum computer as well. You can make any irreversible circuit into a reversible circuit. And there are so this thing that I went through, this exercise that I went through of basically I started from this and I made it reversible. There, these types of things are very well studied. Like the problem of synthesizing functions into quantum circuits is very well studied. And actually, in the upcoming release of Qiskit, we're going to have support for this kind of thing, which is basically you specify a classical function over some Boolean variables, essentially a Boolean function that maps a bit string to some zeros and ones in a classical fashion, and then it gets synthesized for you rather than you having to do it manually like it is here. It gets synthesized for you. But it's an open question, automatic synthesis versus, grabbing things from predefined, well-studied libraries. These are all about tools that are at your disposal to build programs at higher orders of reasoning, and then either you can study like how does each of them behave on a particular quantum device? How do they perform in the presence of noise? How hard is it to simulate each of them? Blah blah. So I will go through some of these examples further. Any other questions that I missed? Okay, great. So yeah, this is already two use cases for a circuit library, which is basically abstracting away the details for you and just giving you a block that you can use, and also giving you alternate implementations of a particular function. And then somebody might say, actually, I have a better way to add on a quantum device. You can actually make contributions to Qiskit, right? So you can put a pull request in for your particular implementation, and then there are automated ways of verifying that this is in fact doing what it claims to be doing, which is like adding two numbers. If it checks out and if it has a lower cost than previous circuits, then it could be a really nice addition to the circuit library. So I say that to mean that the circuit library is an ever evolving thing. So we have an initial implementation, initial release with a few important circuits, but definitely over time it grows and grows. Okay, so just a brief overview of what exists in a circuit library now. So these are like I talked about the adder parts of this, but there are many different things, right? So standard gates, I also see them as essentially circuits. There are circuits that are immutable now, right? So there are circuits that basically do a Hadamard gate, do a swap gate, do an iSwap gate. These are circuits that have a very well defined functionality, but they are essentially, you can think of them as standard gates. Then you have types of generalized gates, so like a permutation on some number of bits. And here the distinction between generalized versus standard might be a little bit vague, but a rule of thumb is that the generalized gates you can give them a problem size, a size of register, whereas these are basically fixed. Arithmetic and Boolean logic are one example. I showed you adders, but there are many other different kinds of arithmetic and Boolean logic circuits. There are these types of end local circuits. So these are specifically very attractive for implementation on devices because it's very hard to get long range interactions on devices. So you always have qubits talking to their neighbors. So when you have locality in the circuits, then you can actually use those in your investigation of some, for example, particular algorithm. You can parameterize them, you can vary the parameters, and you can solve the problem, but they are localized interactions. I have some examples of these upcoming as well. Okay, and then there are some other classes of circuits as well, like quantum Fourier transform, IQP circuits, graph state circuits. There are many of these, so I'll just go through as many as we can cover in today's talk. So as I said, one aspect of the circuit library is that it gives you essentially, you can think of them as functions, right? So in a classical library, like NumPy, for example, it's basically a library of different routines, right? It gives you functions, and you can combine them with each other to build bigger functions. It's exactly the same way for quantum circuits. So a very well-known quantum circuit is the Fourier transform. Fourier transform itself is a well-defined mathematical. So even classically, you can define a Fourier transform, which is basically taking you from the time domain to the frequency domain or backwards, right? So I'm going to show you how the Fourier transform will look like on a quantum computer. So here again, I basically grab it from the circuit library. I say, I give it to me with like some number of qubits here, 6 qubits, and then I just basically draw it. And it looks like this, okay? So then, to illustrate the difference between classical and quantum, I just want to basically show you that these can be kind of used out of the box. So here, what I'm doing is I'm simulating this Fourier transform on a number of input states. So I have a 6 qubit register as an input. So that means I can basically, if you think about the basis states, I can give it from 0, 0, 0, 0 to 1, 1, 1, 1, 1. So 64 possibilities, right? So here I just look at 4 of those, 0, 1, 2, and 3. So I feed in these computational basis states, and I pass it through 2 different functions. One is this quantum function, the quantum circuit, right? Basically, I create a state from that, and I evolve it through this QFT circuit. And the other is I just feed it through a classical Fourier transform that I obtain from, let's say, NumPy, a Python library, right? And these should behave the same. And so I just plot the different behaviors for each of these, and essentially they're exactly the same. So here, these are for different input states: 0, 1, 2, 3. The orange is quantum. The blue is classical. So they're exactly the same. It's just that in quantum you have this constraint of normalizing, so the height is a little bit different, but the behavior is exactly the same. You get the exact same states. On the left-hand side, we have the real part of the amplitudes, and on the right-hand side, the imaginary part. But as you see, again, it's like you can think of these as frequencies, right? So this is a 0 frequency, this is a 1 frequency, 2 frequency, 3 frequency, right? Basically, I feed it a quantum state, and it essentially encodes that into an output state whose amplitudes are this harmonic oscillation. So this is basically, like, I just want to illustrate, it's not very different from a classical function at all. They're basically the same, right? And so now having access to this kind of thing is, you don't have to worry about the details of a Fourier transform, right? And so, like, a Fourier transform, like, there's this well-known way of approximating a Fourier transform by cutting off some higher precision terms. Excuse me. Oh, sorry, yes. Question is, what are the axes of the plot? So these are essentially the 0 to 63, the inputs. So yeah, as I said, you have a 6 qubit register. So when you send that number, send that state through the circuit, out comes a state which is described by 64 amplitudes, right? So these are the amplitudes, the real part of the amplitude and the imaginary part of the amplitude. Okay. So I was going to say, you can actually, so some of these circuits in the circuit library have different options as well. So for example, there's this approximation degree. So for example, implementing this kind of thing on a quantum computer might be too expensive because there's a lot of noise on a quantum computer, and as the noise builds up on all of these gates, you might actually read out garbage in the end. So one way to get around this is to say, actually, some of these rotations are pretty small. So what if I just ignore them, right? So approximation degree, let's say 1 or maybe 2. So it basically chops off those small angles of rotations, and you get an approximate quantum Fourier transform here, which, depending on the level of noise on your hardware, this approximation, you lose something in the approximation itself. However, it might be worth it because you gain something in being the shorter depth circuit. So if I run this approximated version of this Fourier transform, you see some of it is a little bit distorted, right? So I'm running on an ideal simulator, and this approximation error that I incur, so it's not as clean anymore, right? But still, you see the same behavior of the frequencies being encoded into the states, right? Okay. So then, all right. So as I said, what we would really like to do is to use these blocks of computation and kind of combine them into bigger applications or bigger, higher order computations. So to illustrate this, there's this nice paper from Martin Rotler, actually, that describes the Hartley transform on a quantum computer. So a Hartley transform is basically, in signal processing, it's used to transform signals. But it actually, its definition, inside of the definition, it uses Fourier transform. So it uses a Fourier transform. So if you want to do it on a quantum computer, it turns out you have to do it like this. Essentially, you have a block of a Fourier transform. So each of these blocks is basically this whole thing, right? So I'm just boxing it up. So you have a Fourier transform. You have a Fourier transform raised to the power of 2, but actually the application of it is controlled on an ancilla bit. So you have one extra bit here that controls what, if it's 0, this part gets ignored. If it's 1, this part gets applied. Then you have a rotation on that ancilla, and then another Fourier transform raised to the power of 2. So suppose now, so this is not a really standard transform, but suppose I want to encode it, right? So now basically what this tells me is if I have access to the Fourier transform, I should be able to use these boxes, compose them together, and build something bigger, the Hartley transform. And that's exactly how you do it, right? So this is the code to do this in Qiskit. So you have, let's say this is 4 qubits as an example. So this number here, sorry, the register here that I'm doing the Hartley transform on is a 4-bit register, but it could be more, whatever. So then I basically grab from the circuit library the elements that I need. So I need a Hadamard gate. I need a QFT on these number of qubits, and I need this rotation operator, which is basically a 1-qubit unitary gate. And I can basically drop this unitary gate into the circuit. So it basically shows that in a Qiskit circuit, you can combine many different types of elements. You can put in a unitary gate. You can put in a standard Hadamard gate. You can put in a QFT. You can put in, and so like I think in the future circuit sessions, we'll show you how you can add, for example, low-level pulses and things like this. But anyway, and then this is how I compose this circuit. I basically start from an empty circuit. I put in my Hadamard. I put in my QFT. I put in my QFT raised to the power of 2 and controlled. I put in my R operator. I put in, again, my QFT raised to the power of 2 and controlled. And then I put in my final Hadamard. I'm basically following this recipe, right? And this is how it gets built in Qiskit. So this is the figure from the paper. This is what gets built in Qiskit, is automatically drawn in Qiskit, right? And then so then I'm going to do the exact same thing I did with the Fourier transform, which is I'm going to say, all right, the Hartley transform is a classical signal processing technique. So it has a well-defined definition, which is essentially this, right? So you have a cosine plus sine with some period being added together. So I'm going to I can easily code this up in Python myself. So this is a discrete Hartley transform written classically, which is basically, essentially, this is the key part, which is this. All right, so I'm going to do this and save this. This is a classical Python function that takes the Hartley transform of an input x, and that x could be 0, 0, 1, 0, whatever. So now, and then I have a quantum circuit that does this. So I want to verify these against each other to make sure they're both doing the right thing. So then there's a catch here, which is when the Hartley transform is actually only valid for real valued inputs. So you cannot give it complex valued inputs, and quantum states have, their amplitudes can be complex. So I have to be careful that what I feed into this, it has only real valued amplitudes. So one way to do this is I basically want to give it random inputs to test this. Let's say I just want to test that this is correct. I want to test it with some random inputs. So I'm just using this Qiskit function, random state vector, I will build a state vector on these number of qubits in a random state vector. But this random state vector could have complex parts to it, right? And I want to get rid of those. So one trick that I can do is I can basically say, what are the probabilities associated with these amplitudes? And probabilities are real numbers, right? I can convert these to probabilities and then take the square root of the probabilities. Now these are now real numbers. And I can encode that back into the amplitudes. Did everyone get that? So you start with amplitudes, which are complex. You take probabilities, which are real valued, and the probabilities are squares of amplitudes. So you have to stick square roots to go back to amplitudes, which are now real valued amplitudes. And this is what I get. So this is a randomly generated state. And if you see all of these amplitudes, so it's over 4 qubits, so it has 8 entries, and all of the, sorry, it has 16 entries, and all of the entries are real valued. I got rid of the complex part of it, right? And now this is a valid thing that I can feed into my Hartley transform. So I'm going to do the same thing. I'm going to set up the ancilla state, the initial state, which comes from my data state that I created randomly. I evolve it through the circuit. Then this is the key part. You have to take the partial trace because you're essentially interested in reading out only this part, and this last part is irrelevant. It was just a scratch space for computation. This is an ancilla. So in order to trace that out of the circuit, because this, the circuit represents the full state vector as it goes through, I need to trace out this last part. So again, there's a function in Qiskit to take that partial trace of a state. So I get rid of that last qubit, and then I basically get this reduced state, and I get a quantum Hartley transform that is the transform of this. Okay, if I want to do it in a classical way, I basically just call this function that I coded up. So this is the classical part. Now I plot the classical versus quantum, and they're exactly the same. Okay. Oh. Why did I choose Hartley over Fourier transform? So, I mean, I didn't choose it. I'm just illustrating some different examples. So I already showed the Fourier transform, and this is an example. The Hartley transform is an example of, boxing up these building blocks and using them into something bigger. So if these are the boxes or the Fourier transforms, and I'm using them to build something bigger, this Hartley transform. Right. So this is how I'm composing the circuit from these different blocks. I called it like Legos. You're just composing them. Yeah. So anyway, they become exactly the same, right? And so this kind of checks out. Okay. So is that clear? I basically wanted to show a couple. I'm just going through some examples from the circuit library of how different things are used. But obviously, you can study it for yourself, and you can find cool things to do with them as well. So I'm just going to go back to revisit this thing that I did here, which was prepare a random state, but only with real amplitudes. So I did this using this trick of moving them to probabilities and taking the square root of the probabilities. In fact, there is actually a circuit in the circuit library that does this. And this is basically, it looks like this. So I basically grab it from the circuit library. It's literally called real amplitudes. And the reason it does real amplitudes is, so basically the circuit looks like this. So you can think of it as a pattern of a circuit where it's basically rotations, RY rotations, layers of RY rotation interspersed with entanglements. So, and these RY rotations, these numbers are basically parameterized numbers. So you can stick in any parameter there. So this circuit itself, this pattern of a circuit, which is RY entanglement, has uses. You can use it for algorithms. Next week, Julian will talk about using circuits and algorithms. But basically, I'm using them for my own purpose here, which is, as I said, I want to build amplitudes because in order to feed a state to this Hartley transform, I need the amplitudes to be real numbers. So I want to prepare states with only real amplitudes. And so this is another way of doing this. It's really simple. You just grab the circuit from the circuit library, and then I just randomly assign parameters to these RY rotations. As I said, it could be any parameter. So I fill in these theta rotations with like 0.22, 4.3, 4.1, whatever, could be anything. And then I evolve a zero state vector through this zero state vector. I evolve it through the data preparation circuit. And again, as promised, out comes a circuit that has, out comes a state that only has real amplitudes. So this is just another way of doing what I did up here. Of course, this is the circuit way of doing it. Having a circuit like this, where you can vary the parameters, has a lot of use cases, algorithms like variational algorithms, where you want to tweak the parameters, etc. Yeah, so this is just another illustration of the stuff that you can do with a circuit from the circuit library. All right, I'm gonna stop here and see what other questions there are. Hopefully I'm not missing anything important. Okay. All right. So far what we've seen is basically examples of a couple of examples from the circuit library. I showed you how to use adders. I showed you how to use Fourier transform, how to use a Fourier transform inside something bigger to build, like, for example, my own favorite transform, Hartley transform, whatever you want to do with it. So these are essentially using these as blocks that are abstracted away so that I can at least, I don't have to think about the details of each of these things now, right? So I use them as blocks and compose. What other use cases might there be for a circuit library of this kind, right? So as I said, this the circuit library has a lot of different stuff in it right now, and these are examples of things that are really well studied in the literature, and they have particular use cases. So one of the use cases for a circuit, for a particular circuit, could be that it's a circuit for benchmarking, let's say. What do I mean by that? Like, for example, as people are building quantum software, people are building quantum hardware, you want a way to know how good this thing is, right? So for example, myself, I work a lot on compilers. How good is my compiler? I want to have a representative set of benchmarks, circuits, that I can basically test it on my compiler and see how good it is, right? So or like people who build devices and quantum computers, they want to know, can my computer do things that I care about? What are these important benchmarks that people care about? So I'm going to illustrate a couple of these as examples. A quantum volume is a metric that is proposed for essentially full system benchmarking. So it's a type of a circuit. So I'm going to show you what it looks like. I'm just going to grab it from the circuit library and draw it with 6 qubits. So you can vary this number. But basically what it is it's layers of SU4 Haar random unitaries. So this is a 4x4 matrix, essentially. 4x4 matrix, 4x4 matrix. And then these are essentially applied on different random permutations of 2-qubit pairs. So there are 2 sources of randomness. One is how you draw the unitaries here. These are randomly chosen unitaries. And how you choose the pair of qubits to apply them to. Again, these are also randomly chosen. So this is, you can see why this can be a good benchmarking thing, right? Because it's intentionally very difficult to implement, right? So you're essentially having all of your qubits randomly talk to each other. You have these high-level unitaries that need to be decomposed into the native gates of the device. So it basically hits on a lot of the important things that you care about on a quantum computer: the compiler, the fidelity of the gates, the coherence of the device, things like this, right? So this quantum volume circuit, suppose now I want to benchmark it for my compiler, let's say, right? So I want to say, suppose I have 6 qubits within a ring topology, right? And I want to compile this circuit onto this. These connections basically say which qubits are allowed to talk to each other, on which qubits you're allowed to have 2-qubit operations. So 4 and 5, you can have a 2-qubit operation on them. 4 and 1, you're not allowed to, okay? And then suppose my device has 2 types of tuned up basis gates: a control Z gate and U3 gate. The U3 is essentially, you can call it a U gate. Like, it's basically an arbitrary single qubit rotation around the Bloch sphere. And this combined with this is a universal basis. So you can rewrite any circuit, any quantum circuit, in terms of in this basis. okay? So I want to lower it down to this basis, and I want to target this particular coupling map, okay? So, so this transpile function in Qiskit is basically is for rewriting circuits. So I specify my circuit and the constraints that I have on it, and it compiles it, and I get the depth of the circuit and the number of non-local gates. You can see it's actually quite high. So you have a depth of 67 and number of non-local gates 78, right? So this is like, you know, first order, and it's now trying to draw the circuit. It's a quite big circuit when it gets decomposed and mapped into the device. So then you can say, for example, can I do any better than this? So, you know, one recent addition to Qiskit has been this layout and routing paths. They're called Saber, based on a paper by Gushu Lee. And they actually perform pretty well on a quantum volume circuit. So if I just change the layout and routing method for this quantum volume circuit, so remember the depth of this was 67 and the number of non-local gates, which are basically the most expensive gates, are 78. So if I recompile this, it becomes lower, okay? And then I can say, actually crank up the optimization level, okay? It actually goes really low. So this optimization level in the compiler was able to reduce it from something like 68 and 78 down to 37 and 45. And if I draw it, it's a much more compact circuit, something that you can hopefully run on a present-day quantum computer. So again, so I use this as a benchmark of my compiler. It can be a benchmark of the device as well. Another type of benchmark are graph states. Graph states are basically Clifford-only circuits, and Clifford circuits are efficient to simulate, right? Because they're highly entangled, but their gates are from a restricted gate set of only Cliffords. And so when you're within that restricted gate set, you can efficiently simulate any circuit. Actually, before I go into this, were there any questions? Let me see. What are some algorithms that you're looking to add to the library, asking so open source coders can help? Yeah, so I think there's a slight distinction between algorithms and circuits. So you can definitely use circuits in algorithms. So if you're interested in how these circuits from the circuit library are used in algorithms, I would encourage you to watch next week's circuit session with Julian, who's going to basically go through how different types of circuits can be used to do algorithms, let's say in chemistry or machine learning. Oh, that's actually in 2 weeks, sorry. But yeah, so you know, there's a lot that can be added to the circuit library itself. So arithmetic is one area that can be expanded upon greatly. But yeah, I think maybe we can open some issues on the Qiskit GitHub on things that we can help with. It will be definitely appreciated. One more thing, there's a small discrepancy with the classical and quantum output of the Hartley. What is this due to? The approximate. Oh, that's a good point. Let's see. Oh, this discrepancy. I'm not sure that's a discrepancy because I'm using the. I think I'm using the exact Fourier transform here. Yeah, I'm not approximating. I think this is just how it's drawn. It should be exactly the same. It might be numerical errors in the evolution of the state in the simulation, but they should be exactly the same. Okay. So I'll go. Oh, sorry. So one last question. What exactly does optimization level denote here? So this optimization level is something we expose in our compiler. You know, if you're familiar with classical compilers, they have this thing where you say optimization levels 0, 1, 2, 3. And you know, lower optimization levels mean usually that you might get a less optimized circuit, but the advantage is that it will be very fast to compile. Higher optimization levels, you might spend some more time in optimizing the circuit, but if you really care about driving the cost of the circuit down, the number of gates, the depth, then it might be worth it. So this is basically just saying, and in Qiskit, you can set this attribute from 0 to 1, 2, and 3. Okay. All right. So in the last 20 minutes, I'll just go through a couple more examples. So this graph state I was talking about is basically, yeah, so what it is basically it relates a graph to a quantum circuit. And the way that works is suppose you have a graph. Here I use this network X package in Python to generate a random graph. So it's a random graph on 40 nodes, 40 vertices. And this is just something to control how to randomly draw this graph. Okay, so this is a random circuit, so I can, yeah. So anyway, so so there's a lot of use cases that come from these graph state circuits. So in quantum error correction, in measurement-based quantum computing, but as I said, like the circuit itself is easy to simulate, and you can see it from here. So there's this nice widget in Qiskit, essentially a Jupyter widget to draw circuits and have some, so you can invoke this widget on any of the circuits from the circuit library. So this is how the circuit is. You have essentially 40 qubits representing 1 qubit per vertex here. And you have a layer of Hadamards and a CZ gate whenever there is an edge between the two qubits, the two nodes. That's basically how the quantum circuit is prepared. But this widget kind of shows you like the chasm representation of so it's an assembly language representation for the circuit if you care about that. And then some general information like what is the width of this, what is the depth of the circuit, how many total gates. And so this circuit is nice to use in a lot of, as I said, in error correction, in measurement-based quantum computing. So and there are actually works that show, like, for example, if you add layers of post-rotation to this, now it's no longer a classical a Clifford circuit that becomes very hard to simulate. But anyway, here I'm basically I just want to show how we can relate this graph to this circuit and verify that it's doing the right thing, right? So so the reason these are called graph states is because you can you can assign essentially stabilizers to this graph. So the way the stabilizers are built here, so I actually grabbed this function from Julian's code, but basically what it does is you give it a matrix, and you build the stabilizers associated with this matrix. So it's just a matrix goes in. A matrix means an adjacency matrix between. This is a 40 by 40 adjacency matrix here. Whenever there's a self connection, I put an X operator. If I have a vertex, so I have an edge connecting the two vertices, that's a Z operator, and then otherwise an I operator, right? So for every matrix, I can get a stabilizer associated with that. And then somebody comes along and says, actually, I built a circuit that implements a graph state associated with that graph. So I want to verify this. I want to say, did you do the right thing, right? So basically, the stabilizers that describe this circuit have to be the exact same stabilizers as this circuit, right? Because these are Clifford circuits, I can actually efficiently extract the stabilizers from them. So here I have a 40 qubit circuit. Like 40 qubit circuits are impossible to simulate if you wanted to do, for example, like do a unitary simulation or something like that. It's just too large, right? There are 2 to the 40 amplitudes if you want to do a state vector simulation alone. Right. So this is so for a given matrix, I have the stabilizers, and then I have so I have I get this Clifford object from Qiskit, and I say, give me the Clifford representation of this circuit. So what this does is, under the hood, it's simulating the circuit with a Clifford simulator, and it is efficient, as I said. So you have massive 40 qubit circuit, and this whole thing gets run very quickly, and I compare the stabilizers of the matrix with the stabilizers of the circuit, and are they the same? And it checks out, it's true, they're the same. So if somebody, these are the stabilizers if you care about them. But yeah, so if somebody comes along and gives you a different circuit that implements this, you can, instead of doing a very expensive simulation of the unitary, for example, you can basically say, all right, I'm going to get the stabilizers associated with the circuit, the stabilizers that describe this graph, and are they the same? It's very quick. Are you missing any questions here? No, so okay, I have sorry. So the question is, can different circuits from the circuit library be rewritten in different bases? So the answer is yes, as of the latest version of Qiskit that is coming out, I think next week. So you can basically do basis translation from, if your basis is a 1 qubit or 2 qubit basis, then you can rewrite any circuit, as long as there's, as I said, it's a universal basis, right? And can you export any circuit to OpenQASM? Yes, you can. So this is one example of that. So the question is, can a simulation incorporate loss of fidelity in the gates? And the answer is yes. So Qiskit has this air simulator that you can basically grab like this. You go from Qiskit, import air, and then you can, from air you can get a QASM simulator. And then you can make it you can ascribe to it different noisy options, like simulating decay of coherence decay of qubits, or gate errors and things like that. So you can it can definitely simulate a lot of different types and models of noise. And everything I've done here has been noiseless simulation, ideal simulation. Okay. And then I guess maybe one last reason you might care about these different circuits is one very fundamental question that we're trying to answer in this whole field of quantum computing is, what is the computational advantage of a quantum circuit over a classical circuit, right? And so this question has been studied very well from a theoretical point of view, and so there are classes of circuits that really exhibit advantage over classical circuits, at least with some assumptions. And so one of them is this Fourier checking circuit, and so the circuit library has some of these classes of circuits that you can actually basically explore for yourself. So Fourier checking is basically it can be described as the following problem. You have, let's say, two classical functions, f and g. And then you basically want to see how good of an overlap is there between the function f with the Fourier transform of function g. Okay, and so this can be solved on a quantum computer in polynomial time. However, if you want to do this on a classical computer, you cannot do it in polynomial time, basically. So here's an example of that, right? So you have here I'm choosing two very basic functions, f and g. So if it's a Boolean function, that means you can give it these different bit strings, 0, 0, 0, 1, 1, 0, 1, 1, and it gives you one answer, 0 or 1. Okay, so I just randomly chose these. And the way you do this computation on a quantum computer is basically by encoding these functions f and g as oracles, like basically choose two quantum circuits that encode that function, those functions on a quantum computer. And so one easy way of doing that is this so-called phase oracle, which is basically like imagine a quantum operator which has size 2 to the n by 2 to the n for n qubits, right? So for 2 qubits, these are 4 by 4 matrices. And so if you just imagine the matrices are diagonal, meaning everything is 0 except the diagonal entries, that gives you enough entries to encode the full action of the function, right? So what the phase oracle does, it basically is a diagonal operator where on the diagonal entries are either 1 or -1. So it's a 1 wherever you have a 0, and it's a -1 wherever you have a 1. And that just means do nothing for inputs that are that become 0, and give a -1 phase to inputs that are whose output is 1. So it's just a way of translating that classical function into a quantum circuit representation. And so yeah, so basically you can grab this Fourier checking from the circuit library. You can visualize it. You can encode these diagonal operators. Qiskit will take care of decomposing these diagonal operators for you, so you don't have to care about those. And basically, the probability of observing. So if you actually run this on a device or on a quantum computer or on a simulator, the probability of observing 0 at the output is exactly that quantity that you're looking for. So if that probability is high, that's an example of a so-called correlated circuit, meaning that the answer to the Fourier checking problem is yes. And if the probability is low, then it's not. So here I'm just showing an example of I built the circuit. I run it on a simulator. You can run it on a device as well, and so on. But anyway, so I just wanted to give some flavor of the different types of things that are in the circuit library. Next week, as I said, Julian Gacon is going to talk about using these circuits in an algorithm. So if, again, I said next week, but in 2 weeks. So if you're interested in basically quantum algorithms that solve some task in, let's say, chemistry or machine learning or whatever, you can definitely tune into that one as well. Okay, so I think I'm done. I lost my YouTube link, so I don't see questions anymore, but maybe Paul can help me. Does optimization of reducing gates always help with runtime? So I guess runtime is a proxy for optimization. Let's go back to this quantum volume example, right? Yeah, so on a classical computer, what do you care about? You care about runtime. Obviously, you don't want your program to run forever. You want it to be fast. You want maybe sometimes you care about power consumption. Maybe you care about memory usage, right? On a quantum computer, really the main enemy right now is noise and errors. So what you're trying to do, yes. So what you're trying to do is basically to combat noise. And so more gates, if you have more operations in your circuit, that's more opportunities for gate to build up. So reducing the depth of the circuit, reducing the number of gates in the circuit definitely helps with that. But it's a sort of a proxy for that. So what you really care about is to actually see what the noise contribution to the circuit is. So yeah. Okay, any thought on ZX calculus and whether it can be used for reducing circuit complexity? Yeah, so I think ZX calculus is a nice, basically graphical formalism for describing circuits, and then you can do some optimizations using them. I think it definitely has potential. I think there was a study of looking at it versus the other optimizations that are in Qiskit. I think it's TBD how much utility you can get from it. But I mean it's a method. It's a method, and it's definitely useful. I think there are open source packages actually out there that allow you to use ZX calculus to, for example, like you feed it a QASM program, and it gives you it gives you a reduced or more compact version of that. But I think last time I looked at it, it did not accept all forms of QASM. So maybe it has changed right now. But anyway. Any ideas for projects for intermediate level students? So, okay, that's a great question. Depending on how much time you have. So if you go to the Qiskit GitHub, there are a lot of open issues ranging from, there's a bug somewhere, or actually like there's this feature that we want to implement. And so some of these are tagged with good first issue, meaning if you're not familiar with the code base, maybe like whenever you come to a new project, there's some learning path, right? So these first good projects are really nice to sort of get your feet in the water. and sort of get familiar with one aspect of the code base. They're usually not that hard to solve once you spend some time looking at it. So those are good first issue tags. And then there's another tag, I think, called short project or good short project. And basically that one is for if you want to do something for like a month or two. Then, maybe implement some particular optimization method, or maybe I'll implement some, so there are different types of, depending on how much time you want to spend on that. If you want to, but also like if you want to work on something, let's say for a semester thesis or something, we would definitely be interested in helping and mentoring. And so if you on the Qiskit Slack is a good place to ask. On Qiskit GitHub might be a good place to look at the issues and sort of assign yourself to it. Yeah. All right. I think that's all the questions. Thanks everybody for tuning in today. And as I said, the next Qiskit circuit session is in 2 weeks. That's going to be really useful to follow on to what I described here today. And just generally, if you subscribe to the YouTube channel, you'll get notifications on future events and talks. Okay. All right. Thank you.